Hello, my name is Ines Lindner. I'm a member of our Department of Econometrics and Operations Research. Let me briefly introduce to you the course Mathematics in Economics and Society. You see, in modern economics and society, there is no way we cannot discuss networks or the term complexity. Why is this? Well, for example, I think you all have a Facebook account, and finding a job nowadays, this is not an anonymous market as classical microeconomics tells us, or classical macroeconomics. This is via LinkedIn, and so networks have an important part of today's modern economics and society. Let me just briefly show you some example of networks and tell you why this is important. So here, for example, is a very interesting data set from the US. This is from a high school of 2008. And what you can see here is, so the nodes are people, and the links are friendship, and the green are the Asians, blue are blacks, red's Hispanic, yellow the whites, and there are some others. And what you can see here is an interesting phenomenon called homophily. That this phenomenon means that you tend to end up be friends with people who are similar to you. So, for example, if you're female, it's very likely that the majority of your friends is also female. If you like sports, then most of your friends will like sports. If you are very religious and a Christian, then most of your friends will be very religious and Christian. Things become even more extreme if we ask for strong friendship. So who is your best friend? Then we see this homophily effect even stronger. And well, why is this important for an economic or societal perspective? Well, for economics, for example, what we see here, because of this high so-called clustering, as we can see here, for example, or here, so we see many times that they have a kind of fashion trend, a music taste, and they have as well. They are all at LinkedIn, and they have another community site, and so on. So from an economic perspective, we can explain a lot, and we can also give, from a marketing perspective, advice of what to do. For example, if you want a product that is very spread here, how can we make it travel the bridges to this other cluster? Here's an interesting example of a strategic network. This is data from 1430s, from the Florentine marriages in 1430, so the marriages in Florence in Italy. And what you see here are the wealthy families from that time. And the historians always ask themselves, how come the Medici family that you see here, how come the Medici family became so powerful? Because initially they started with a very small, they were not the richest. And the answer is simply networks, games on networks, because the Medici managed to arrange, so the links here are marriages with other families, and the Medici just have a very powerful position in this marriage network. And from a mathematical point of view, we can show this because if we come up with measures, mathematical measures that actually quantify influence, that indeed, so here is the so-called betweenness measure, then indeed, when measured by the so-called betweenness measure, the Medici family were far the most influential. Here we have another measures, the Strozzi, for example, but the Medici are definitely the highest. This is also a very interesting data set, the structure of romantic sexual relationship at Jefferson High School. So the pink nodes here are girls and the blue are boys. And the links means they have sexual or romantic contact. And the interesting thing is that these kinds of networks, they look completely different to the strategic network I showed you before from the Medici, from the marriage networks. And they actually look pretty much like networks that are so-called random. So this is exactly the kind of network structure. So this very tree-like, then we have here a so-called giant component. And this is exactly the network structure if people just not strategically build links, but just flip a coin in their head. So shall we have a romantic or sexual relationship? Yes or no? I flip a coin, and then there's the answer. And of course, the network structure is very important to address questions like how shall we prevent diseases, how shall we make sure that some information spreads around, that we are a little bit intimate, and so on. This is interesting data from a paper of Matthew Jackson. So the idea was that they offered in Karnataka in the south of India, they offered microcredits, so a very small amount of money that you can lend, and they want, and people find it scary in the beginning because they live in the countryside and who the hell is offering me some money? And what they try to do is they try to address the problem, how can we make sure that this idea of taking a microcredit diffuses as much as possible? And in order to address this, they try to sketch the interaction network. So, for example, they ask people, whom are you going to temple with? And for example, if this is a household, they are connected to this household. They said, like, I'm going to with this family to the temple. If you have to borrow or lend some money, who would you approach for this question, and so on. And by having a map of the social interaction or these networks, they were able to make a prediction of what to do best if you want your microcredit idea to diffuse. So basically, we have three areas for research. We have the theory, how networks influence behavior, cooperation, information diffusion, and opinion formation, for example. And what we always find very interesting from a mathematical economics perspective is that how shall we address networks? What kind of mathematical toolbox shall we use? Shall we work with graph theory? Shall we use with so-called random graphs where we have statistical tools or Markov chain theory? Or shall we work with deterministic methods? And another very important question is, of course, do the right networks form? So this is very important for policy implications. So we want networks to prevent diseases. We want networks to transport information. We want cooperation networks that are as efficient as possible, and so on. Another aspect is the empirical and experimental work, so observe networks, patterns, and influence, and test the theory where developed and identify regularities. This is also where getting a grip on complexity comes in. And the last part is the methodology, how to measure and analyze networks. For example, here we discuss what is the right kind of model, how can we express mathematically how influential somebody is, can we measure this? Here's a short example of what a master student of mine did. So we had, this was a cooperation with the social sciences, and they had Twitter network data. And the main research question was, what are the network structure under avalanches? Avalanches, what we mean by avalanches, we mean these hypes that Twitter subjects overnight get very popular. And can we forecast and control avalanches? So, for example, one main finding was that we have this typical random graph structure, this tree-like structure, so very specific for Twitter. And to forecast and control avalanches, we tested several models to predict them. And interestingly, if you want to do short prediction for just a few days, for example, the random graph models, they perform better. And then if you have from 1 week to a month, then the so-called multi-agent models perform better in predicting, and then the random graph takes over. And we don't have yet an explanation for this, but it's going on research, and we are cooperating also with the people from computer linguistics, because we strongly believe that the content of the Twitter has an impact also of predicting avalanches. So, for example, if hate or love, so if the emotion or sentiment, as they call it in finance, is very high, then this should trigger more avalanches. So this is a short overview what we do in this class. In the first week we talk about networks, how to approach networks mathematically, and we will learn a little bit about how networks form. In the second week, we discussed diffusion. So, for example, diffusion of diseases or diffusion of innovation. How come some innovations spread and how come some others are not? In the third week, we will talk about social learning. So, how does information travel through a social network, and what can we do in order to enhance that? Week 4 to 6, we will talk about deterministic networks. So in week 4, this will be about cooperation and communication. So you have a communication graph or a networks of best buddy, for example, or a network of political parties. And can we actually measure, or can we actually say something about if they work together, how shall we allocate the profit? In week 5, we talk about operations research games on networks. So, for example, we have, if you take as an example the Star Alliance example, where the network is the root. Star Alliance means the cooperation of, for example, Lufthansa, Air France, KLM, I think is also in the Star Alliances. And if I take over your flights, how much do you have to compensate me and vice versa? And there are some allocation rules, as we call them in economics. And what do the design of these education rules, what effects do they have on the incentives to join the Star Alliance, for example? And are they fair? And the last one is a digraph competition. So a digraph is just talking about a directed graph. So, for example, if you take websites, a website pointing at another website means there is a directed link from one website to the other. And if you have these directed graph, can we say something about which website is the most influential one? So we will talk about Google PageRank, for example. But you can also use this in sports, for example. If Ajax beats Barcelona, then there will be an arrow pointing from Ajax to Barcelona. And then we can talk about who should be the winner if we have this digraph given.